Hi, this is John Vise for Edinburgh Explorations, put on by the School of Mathematics and also the School of Physics and Astronomy at the University of Edinburgh. And this is the second part of my series on the standard model of particle physics, our main theory of particle physics. Last time I went through the different particles in a somewhat historical way, talking about how they were discovered. And I sped up as I went along. And in fact, I got going so fast that by the time I said, okay, now I've introduced the whole cast of characters, I'd actually forgotten the last big one to be discovered, which is the Higgs boson. So I'll have to go back through that and put in more detail about how those particles were discovered. But today I want to do something different. I want to talk about the concepts behind the standard model, because those are actually even more interesting than the various particles that have been found, at least for me. And so what I want to do is give not a historical account, but a conceptual account of how we could have developed the standard model, starting from the three big pillars of physics back in the late 1800s, before we had special relativity and quantum mechanics. So let me try to start out by saying what those three big pillars were like. I'll write down a few equations just so you know that there are some equations involved, but don't worry about them too much. I'm not going to explain them in much detail, and you don't need to pay attention to them if you don't want to. So, okay. So the first pillar is classical mechanics, which in some sense was first introduced by Newton, although everything has predecessors. And if we wanted to write down one equation to describe classical mechanics, I guess we'd have to say it's force equals mass times acceleration. So force and acceleration are vectors. They have not only a magnitude, but they point in some direction. So we draw a little arrow on them. And we use this equation to figure out actually the acceleration that a particle feels if we put some force on it. Now, this subject was developed a lot after Newton, in particular by people like Lagrange and Hamilton, who developed deeper approaches to classical mechanics. But moving right along, what's the second pillar? Well, I'd say it's statistical mechanics. So statistical mechanics shows up when you're dealing with so many particles using classical mechanics that you can't keep track of them all individually, like millions or many more particles than that. And so you use statistics and probability theory to say what you think they're doing probably. So you calculate probabilities. And the basic tool for doing it was introduced by Boltzmann, which is a formula for entropy. So entropy, which for some silly reason is called S, is a measure of our ignorance of a situation. And it's equal to minus the sum over all possible states the situation could be in. So I will sum from 1 to n if there are finitely many different possibilities for how things are. And what we sum up is the probability of the ith state of affairs times the logarithm of the probability of the ith state of affairs. So I actually wrote a book called What is Entropy that explains this in quite a bit of detail. And the thing you can do with it is figure out properties of things like gases and other substances. Assuming classical mechanics is correct, you can just combine it with classical mechanics and figure that stuff out. The third pillar is what are called Maxwell's equations because he was so important in developing them. But a lot of people, other people were involved too. And another good name for it is electromagnetism, the theory of the electric and magnetic fields and how they interact with matter. I'll just write down Maxwell's equations in the form that was introduced later by heaviside. So just to give you a flavor for what's going on, so there's something called the magnetic field, which for some silly reason is called B, and it's a vector field. So at each point, it's a little arrow in space. And one equation says that this magnetic field doesn't spread out or diverge, point outwards from any point. And so people who invented electromagnetism invented this concept of the divergence of a vector field and said in an equation form that the divergence of the magnetic field is zero. There's also the electric field, and the divergence of the electric field is not necessarily zero. It's equal to the charge density, the density of electric charge at that particular point in space. So this equation holds at every point in space, and it says that the electric field points outwards at an amount equal to the charge density, which is this Greek letter rho here. There are also equations that describe how the electric and magnetic fields curl around. The electric field curls around at an amount equal to to negative the time derivative of the magnetic field. So this funny upside down triangle and a cross here means curl, and the curl of the electric field is minus the time derivative of the magnetic field. And so what this means is that a changing magnetic field will make the electric field curl around. Similarly, there's an equation saying how much the magnetic field curls around, and this is the most exciting equation in a way because it was the last one to be discovered. So first of all, it curls because of electric current. So J is a vector field called the electric current, and what Maxwell discovered is that there's an extra term in this equation which says that the magnetic field also curls around when the electric field changes. So there's this time derivative of the electric field that gets added on here. So from these four equations, you can show that if you have a wiggling electric field, it will make the magnetic field change, and then the changing magnetic field will make the electric field change, and so on. And so they both cause each other to wiggle, and those wiggles move along, and that's light. And in fact, Maxwell was able to calculate the speed of light from these equations. I'm leaving out some constants in these equations. I'm working in units where all those constants are equal to 1, so we can focus on the simple facts. So for example, I'm not sticking this constant that's often seen here called Boltzmann's constant, and I'm not putting some other constants in here. But anyway, using those constants, Maxwell was able to calculate the speed of light, which is a big triumph. So these are great theories, but they have conflicts that led to paradoxes, which became important when people tried to go beyond these theories. So one paradox or problem shows up when you try to combine statistical mechanics and electromagnetism. You can try to figure out what will happen if you have an empty mirrored box at a particular temperature. If you have a substance at a particular temperature, it will maximize entropy subject to a constraint that the energy in the box is of some fixed amount on average. You can maximize this entropy if you're lucky, and then use that to calculate what probabilities of being in some situation or another maximize the entropy. So people tried to do that for a simple box of light, and they discovered that they got an infinite answer. Now here I'm writing a finite sum over possible situations, but with a box of light, there's actually an infinite sum because light can wiggle in various different wavelengths. And so there are just infinitely many kinds of wiggles that you can stick inside a box. And so the sum is a sum over infinitely many possibilities. Now, sometimes infinite sums converge to a finite answer, like 1 plus a quarter plus a ninth plus a 16th adds up to pi squared over 6, as it turns out. But this particular sum did not at all converge. And so they got what's called the ultraviolet catastrophe. The ultraviolet catastrophe says that actually you would expect more and more light of higher and higher frequencies to be present in a box of light. And that's not what's seen, and it's also just inconsistent because it leads to probabilities that don't sum up to 1. So that was a problem. That problem was eventually solved by the invention, or you might say discovery, of quantum mechanics. Max Planck showed how to get rid of the ultraviolet catastrophe and get the correct distribution of light of different frequencies in a box of light by assuming that light could not have arbitrary energy, but that light of a particular frequency could only come in packets that have some fixed minimum amount of energy. Planck didn't really know what he was doing, actually, and Einstein came along later and really clarified the situation by taking these packets of energy seriously, and he called them quanta, which means packet or unit, and that was the beginning, one of the beginnings of quantum mechanics. Quantum mechanics is incredibly rich and elaborate, and I won't even try to write one equation down here to summarize it, but I'll talk about it a lot more as we go along. Now, there's another conflict that arose between our 3 pillars of physics, which is the conflict between electromagnetism and classical mechanics. Namely, suppose you have an atom, suppose you have an electron orbiting around a proton. They're opposite charges, so they attract. And classical mechanics says something about what should happen. But when you combine it with electromagnetism, the moving electron, you will predict, should emit light, it should emit radiation, and thus it will lose energy, and then it will spiral down into the nucleus, into the proton in this case. And it will happen extremely fast, which is not at all what we see. So what you get is a serious problem, namely you get the prediction that atoms are unstable. You get unstable atoms. So that's a serious problem for combining classical mechanics and electromagnetism. And it turns out that that is also resolved by going to quantum mechanics. In classical mechanics, you can know both the position and the momentum of a particle arbitrarily well, and so it makes sense for the electron to move in closer and closer to the proton. But in quantum mechanics, you discover something amazing, which is that if you know a lot about the position of something, it's impossible to also know a lot about its momentum. This is called the uncertainty principle. And in particular, that principle is not just a principle about our knowledge, it's a principle about how the world actually is. And so it turns out to be impossible for the electron to collapse completely down into the nucleus. It has to be spread out. That is, its probability function, the probability distribution that describes where the electron is, has to be smeared out. And that saves the day. And in fact, it does more than just solve that problem. Quantum mechanics actually predicts the correct energy levels of electrons in atoms, meaning that electrons can't have just any old energy the way they could in classical mechanics, but their energies come in at discrete levels when they're bound to an atom. So that's another kind of discreteness in addition to the discreteness of the photons that showed up in quantum mechanics. So all that's very interesting, but there's yet another major problem that happens when we combine electromagnetism and classical mechanics. This is actually not quite a contradiction between those two sets of equations that I've written down here, but it's more of a contradiction between the infrastructure of classical mechanics and that of electromagnetism. So now in classical mechanics, we had assumed that if you throw a ball at 30 miles an hour while you're running at 20 miles an hour in the same direction, that you have to add those velocities to figure out how fast the ball actually goes. And it will go 50 miles an hour. Sorry for using the archaic miles. I'm American and we're still stuck on miles. I should say kilometers. But the point is the velocities add in this simple manner in the worldview of traditional classical mechanics. That goes against some fact predicted by electromagnetism, which turns out to be true, which is that even if you're running along, if you shine a beam of light out in front of you, the light will go no faster than if you were standing still. Light emitted from anything always moves outwards in all directions at the same speed, called the speed of light, not surprisingly, and it's not affected by the motion of the object that emits it. That led to a serious conceptual problem, which we might call the speed of light paradox. And Einstein thought very hard about that and invented special relativity to solve that problem. So this led to special relativity. What's special relativity? Well, it's a whole new outlook on what space and time are. I'm not going to fully explain it, but the basic idea is that before special relativity, we thought of space and time as separate things. And in particular, the concept of distance only involved space. And there's a formula that says that the distance between two things is the square of the change in their x-coordinate plus the square of the change in the y-coordinate plus the square of the change in the z-coordinate. This is the three-dimensional of the Pythagorean formula that you might have seen more in 2 dimensions. What Einstein realized was that this was wrong because it doesn't take time into account. If there's also a change in time between 2 points, that is, if one point or one event, we might call it, happens after another, then the change in time squared also shows up. And in fact, it shows up with a minus sign like this. Normally, we put the number c squared in here, that's the speed of light squared, to convert between the units of time and space. But I've resolved in this little mini presentation here to leave out various constants of nature by working in units where those constants are equal to 1. So that just makes everything more conceptual and pretty. So let's just leave out that c squared there. It's secretly there. We're just working in units where it's 1. And this is the new improved formula for distance squared. Well, this is so different than the old idea of distance. For example, it can be negative that we don't even want to call it distance anymore. It's something like distance, and it just is distance when the change in time is 0, but it's something more general. And so a common name for it is interval rather than distance. And so the idea of special relativity is that space and time are a unified whole. A point in this new unified thing, which we call space-time, tells you where something is, but also when it is. And the correct way of measuring intervals between them, between 2 events, is this formula here. And from that, you get a lot of interesting stuff coming out. So this is the early 20th century landscape of physics when special relativity and quantum mechanics had come along, and people wanted naturally to use special relativity and quantum mechanics to better understand the world. And so in particular, you need to combine those two insights of quantum mechanics and special relativity to get a new improved version of theories like classical mechanics or electromagnetism. And this new improved approach is called quantum field theory. Now, the first quantum field theory to be studied was called quantum electrodynamics. Quantum field theory is really just a general framework for building physical theories, just as classical mechanics is a general framework. But you have to give it some specific content to describe a specific situation. And if you're trying to describe the electric and magnetic fields, you need to adapt Maxwell's equations to this new worldview where you're taking quantum mechanics into account. So quantum electrodynamics is quantum field theory applied to electromagnetism. So once you have figured that out, however, you're not anywhere near done because there are other forces in addition to the electromagnetic force. So last time I briefly talked about them. These weak and strong nuclear forces are the two other forces that are readily apparent when you start studying nuclei and how nuclei can change into each other, how neutrons can turn into protons, and so on. So the standard model should go beyond quantum electrodynamics, and it does, but it involves some new insights. And these new insights actually come from pondering electromagnetism a bit more deeply. And these new insights go by the name of gauge theory. So gauge theory resulted from re-examining Maxwell's equations and thinking about them more deeply. In particular, it turns out that the electric field, well, let me do the magnetic field first. The magnetic field is not really the fundamental thing. It's really the curl of some more fundamental field called the vector potential, written as A. It's a vector field that we call A, or the vector potential. What does this all mean? Well, it turns out that to understand this vector potential, you need to actually think about quantum mechanics, although people were already working with it before they had quantum mechanics. But quantum mechanics says that the vector potential is our way of describing how the phase of a charged particle will change as it moves through space. I haven't talked about how phases are important in quantum mechanics. I haven't even said what a phase is. I'll have to do that. But it's a fundamental notion in quantum mechanics that any system has a phase which can change. And as a charged particle moves through space, its phase changes according to this vector potential. And so because the magnetic field is the curl of the A field, it turns out that the magnetic field just tells you how the phase of a charged particle changes when you move it around a loop in space. Similarly, the electric field there is not the fundamental thing. It's actually the time derivative, or more precisely, minus the time derivative of the vector potential, but then also minus the gradient of some function called the scalar potential, sometimes called the electrostatic potential. What's that? Well, it turns out that the good way to understand the scalar potential is to think of it as the rate at which the phase of a charged particle changes as it's moving forwards in time. So the vector potential tells you how phase changes as you move through space. The scalar potential tells you how phases change as you move through time. The electric field, turns out, tells you how the phase of a particle would change if you could move it around a little loop in space and in time. So there's a lot to say about this. In fact, I wrote a whole book about gauge theory called Gauge Fields, Knots, and Gravity. But I'm not going to get into that now. I just want to say that this is a new outlook on electromagnetism. In particular, one thing it does is this, that if you accept that the magnetic and electric field are given by these formulas, then two of the Maxwell's equations become automatic. Namely, it becomes automatic that the divergence of the magnetic field is zero, and it becomes automatic that the curl of the electric field is minus the time derivative of the magnetic field. So the two Maxwell equations that don't involve matter, that don't involve the charge density and the current, they just follow from this new outlook. So we're getting kind of simplification showing up already. But the really important thing about gauge theory from the point of view of modern physics is that you can generalize it from the case of electromagnetism to talk about other kinds of forces. And this was done by Yang and Mills. And so their generalized version of Maxwell's equations are called the Yang-Mills equations. And this kind of theory is called the Yang-Mills theory. So you could describe Yang-Mills theory in a purely classical way, just like electromagnetism existed before quantum mechanics. But in fact, historically, it came after quantum mechanics had been introduced, even after quantum electrodynamics had been introduced. So people immediately started thinking about the quantum version of Yang-Mills theory. So you could think of it as a combination of quantum electrodynamics and the insights of gauge theory. Now, the beautiful thing is that Yang-Mills theory describes all the forces we know of in nature except for gravity. So not only does it describe electromagnetism, it describes the strong nuclear force and the weak nuclear force. And those three, electromagnetism and the strong and weak nuclear forces, are the forces that are discussed in the Standard Model. So the Standard Model is built on the back of Yang-Mills theory, and it's a special case of Yang-Mills theory. It has some additional ingredients, notably the fermions, like the quarks and leptons, and also the Higgs boson. So they are all fit in there in a certain way. So that's the story of how, from the three pillars of late 1800s physics, we arrived at the Standard Model. There was a lot of experimental work in doing that, but here I'm focusing on the conceptual side of things. Namely, just by thinking about these three theories, you could have noticed that there was a speed of light paradox when you try to combine classical mechanics and electromagnetism. You get unstable atoms when you try to combine classical mechanics and electromagnetism. And you get an undefined situation when you try to study a box of light at a fixed temperature, combining statistical mechanics and electromagnetism, the ultraviolet catastrophe. And the resolutions of those problems led us, or could have led us, and to some extent did, in fact, historically lead us to quantum mechanics and special relativity. And then once we understood quantum mechanics and special relativity well enough, we could apply them to generalize the insights of Maxwell's equations in electromagnetism to the other forces and get the Standard Model. Now, I have to somehow try to explain this stuff to you in more detail in the lectures to come. There's too much to talk about. It's just way too much for me to get around to talking about in any reasonable amount of time. So I'm going to have to be tactical about it. And I've decided that the thing I have to focus on most of all, first of all, is quantum mechanics. I haven't said much about the meaning of quantum mechanics compared to special relativity. And that's because it's harder to explain. And so that's what I'll do next time. I will start explaining quantum mechanics. And we'll develop quantum mechanics along with enough of the math of it so that we can understand the particles in the Standard Model. Particles in the Standard Model rely on some reasonably simple mathematics, but it's very strongly quantum mechanical mathematics. It's the kind of math that you would only get interested in if you're either a pure mathematician or you want to understand particles. It's deeply quantum. It's very unfamiliar to if you're used to things like tables and chairs. And it's beautiful. Like these fundamental particles are mathematical jewels. Each one of them is a jewel. So I will begin explaining quantum mechanics next time, and I hope to see you in part 3 of this series where I'll do that. Thanks.